Okay, this lab is to show you how to use the state space method to describe an electrical system. Okay, so basically a state space model is a n first order coupled differential equations. Okay, so basically we have a first order equation and a linear equation. Okay, but all variables in these equations are vectors and matrices, not just simple one single variable. Okay, so this is a vector matrix form of the state space. Okay, and X is one of the vector, n by 1 vector. N is the number of total variables in the system, and U is a scalar representing the input, especially commonly a force or a torque or something like that, like an initial input, like a step input or an impulse input, something like that. And Y is a scalar representing the output. Okay, and the matrix is A is n by n. Okay, and B is n by 1, C is 1 by n. So this is a linear algebra calculations with first order coupled differential equations. Okay, so an example is simply like this. Before we do the example, the transfer function, you can always derive the transfer function from this state space. Okay, so as long as you have A, B, C, and D, you can get the transfer function through this. All right. And this is the time response given you have A and B and so forth. Okay. And this is an example. It's a very simple RLC circuit. This is the input. Okay, current source, step input, and this is capacitor, inductor, resistor, and we can use the KCL and KVL to write the equation like this. So these two are the first order differential equation of the state space modeling. Okay, and by assigning VC equals to x1 and IL equals to x2 and convert this, and we can do like x equals to x1 and x2. Okay, and then we can have we can write this equation like this, and then we need to calculate this y, which is the output. Okay, so by converting the equation, or say rewriting this equation 4 to equations 5, and we can get A equals to this, B, C, and D. And as long as we have this A, B, C, and D, we can write, we have all the necessary coefficients for these two equations. Okay, and what we need to do in the MATLAB is to use this A, B, C, and D, and use this SS A, B, C, D to build up a state space modeling. Okay, rather than using the TF, if you still remember in the previous lab. Okay, and then we can use the step of this system or the impulse of the system to generate the step response or the input response. Okay. So basically, this is an example of how to use the state space modeling to describe a circuit or a system in compare with the transfer function. Okay. And always remember that the transfer function can be derived from this state space modeling or equations, and vice versa. In this lab, what you need to do is, first of all, to show how to derive the state space to the transfer function. Okay, and then run the LT-SPICE simulation of system 1, which is the RLC circuits, and compare the results of step response that you have in the MATLAB. Okay, and the next two are the other two examples you need to practice. So first of all, you need to derive the state space modeling for both circuits, or systems, system 2 and system 3, and then use the MATLAB to find, not use the MATLAB, you need to hand calculation the A, B, C, and D, and use the MATLAB to build this as state space A, B, C, D, okay? Which equals to the system of these two systems respectively. Okay. And you also need to run the LT-SPICE simulations to compare the step or the impulse response of both systems. All right. So basically, it's just give you some practice on how to use the state space and to compare the transfer function results and also the LT-SPICE simulations.